I'm not able to hear. Say something, yes or no.
No, sir.
Good. Okay, so let's start today's lecture, lecture 13 for our Advanced Electric Drives course. And we are now discussing the realization of voltage source and current source converters. And after discussion on induction motor and what we need actually to run induction motor, we have realized that some way we need to generate variable voltage, variable frequency kind of output voltage. So which is possible through the power converter. So this could be a DC to AC power converter where we have DC input and then AC as output, which we can vary the voltage and frequency, all these things. Now, how to exactly generate the required voltage, that we will see. But as of now, let us understand what is the meaning of DC to AC power conversion. And this is what we are ultimately trying to achieve, that if we want to convert DC voltage something like this to AC voltage. So this could be a very crude way. So fundamental can be something like this. So it's not close to sinusoidal voltage, but at least we are able to generate the AC output voltage. So that's enough as of now. We will see how to improve the quality and other things. So now this is possible through this kind of arrangement where we have two SPDT switches and this is single phase power conversion. And four possibilities we have seen that we have. If we connect opposite terminals for both poles, then it is plus Vg. And if we reverse that, let's say A, A2 and B, B1, it is minus Vg. And if you are connecting to same terminals, let's say same DC bus on both the sides, then it is zero output, and same DC bus on the negative side, then also the output is zero. So maybe a little bit better waveform which can be generated here actually with this kind of arrangement. So why it is better? No, what parameters say that no, this is a better quality? These things are for our next class. But today we will see how this can be realized through switches. So then we have gone on to see that how three-phase system can be realized. So we do not need 6 SPDT switches, but 3 SPDT switches are enough for three-phase system. And we do that power conversion on per phase basis. So we take a fictitious point at the middle of the capacitor bank. And with respect to that, we generate the output voltage, say VRO, VYO, VBO. So what you will find that if we are generating balanced output with respect to the point O, then the line to line voltage is automatically generated as balanced supply. So VRY, VYB, VBR will also be of this AC nature and these will be balanced in three-phase format. So shifted by 120 degree from each other. So this is what we have seen. And then we saw the one more level we have increased in our output. So earlier we had only two level. So when we say output, we are particularly talking about the output voltage with respect to the capacitor midpoint and which is called pole voltage. So pole voltage VRO, VYO, VBO. All three have only two levels, either plus VDC by 2 or minus VDC by 2. So hence the name two level inverter is coming. And because it is fed through a voltage source or voltage stiff element, say capacitor, so this is called voltage source inverter or converter. Both terms are perfectly all right. Now we can introduce one more level in our output voltage, say a middle point 0, by introducing one more terminal for connection with the pole. So earlier we had only two throws, now we have three options available for the pole to be connected. This R can connect to R1 or R2 or R3. So this is basically a single pole triple throw switch. Now if this kind of arrangement is there, we can generate this plus VDC by 2 or 0 or minus VDC by 2. So waveform may look like this. Okay, something like this it is generated where we have plus VDC by 2 level, 0 level and then minus VDC by 2 level. This kind of arrangement we are having. Now let us move to say we want to generate further a few more levels in our voltage source converter, say a 5-level converter or 4-level converter. So similarly, we can introduce more options for the pole connection in our throw side. So let's say we have 5-level converter to realize. Now, what could be the possible voltage levels for our output, say VRO? Obviously, 0 can be there because odd number of levels are there. So middle point could be 0. Then highest could be plus VDC by 2 and lowest could be minus VDC by 2. There is no doubt in that because we have middle point as 0. Then additionally, we may have two more levels, which is called VDC by 4 and minus VDC by 4. So this way we can have 5-level converter. So now because we are having 4 or 5 voltage levels over here, so we need more division for the input voltage. So which means more connections on the capacitor side. So earlier we had only 2 for a 3-level converter. For 5-level converter we may have 4 capacitors, and then each of these points are taken out. These are all possible connections for the pole. So if you give these terminals some names, say R1, R2, R3, R4, R5, so we have the possibility for R to be connected to any of these, R1 to R5. And based on where we are connecting, we may have different voltage levels. So I can just mark quickly on this. So this is basically plus VDC by 2 connection. The second is plus VDC by 4. The third one here in the middle is 0. And the fourth one is minus VDC by 4. And here it is plus VDC, sorry, minus VDC by 2. And each capacitor is having equal voltage. So earlier it was VDC by 2. Now here each one is having VDC by 4. So making the total voltage across DC bus equal to VDC. So now our voltage waveform, what we will generate from this converter, may look like something like this. Not necessarily that it has to be like this, but one example could be something like this. So these voltage levels are what we have generated. And so on. So to say like this is a further better quality of waveform compared to what we have seen in case of 2-level and 3-level. We will discuss why. But as of now, just understand this, that in general, the perception is that if you have more number of levels in the output voltage, here we are talking about the output voltage with respect to the DC bus midpoint O, which means the pole voltage. So then what we have is that the quality of the output voltage is better if we have more number of levels. We will see why. Okay, now this is about voltage source converter. Then we may have option to have current source in the input side. So if we can have battery and capacitor, all these arrangements, why can't we have current source on the input side? Yes, we can have. And if we are having current source, definitely this is a DC current, right? It cannot change its direction. Now what we want to have conversion of this DC input current to AC input current. So something like what we have done in case of voltage source, this IG should be converted to IO of this nature. Now, what are the options? Again, we are going to use something similar to SPDT switch or maybe SPDT switch for this realization. Say, first we talk about single phase. Now, definitely when we have current source, the pole is going to be connected to the current source end, which means this is the pole. So say A and B. And then this can connect with, say, either one option here or one option here. And between these two, we connect our load. So say this is A1, A2 and B1, B2. So when you are having connection like A1 and B, B2, the current will flow like this through the load. Through the source, current direction is fixed. And when you connect A to B1 and okay, so let us call this as A2 and this as B1. When you connect A to A2 and B to B1 here, then the current direction will be like this. So we are able to change the direction of current, and to avoid any high transition currents and voltages, we can connect a capacitor across this. So making this element as voltage stiff. So we can have a capacitor between the terminals of the load when we have current source converter feeding this. So you are getting this point here. Again, we have one more possibility that we can connect A1 and B1. In case of the current will flow like this, shorted through the source itself. That time the load will have I equal to 0. And another option, when we have A connected to A2 and B connected to B2, again we are shorting the current source in itself, so we have 0 current for the load. So this is how we can realize the current source inverter, again by having a single pole double throw switch connected like this. Now here we have this single pole double throw switch and this single pole double throw switch. Correct? Any confusion in this? So whatever rules we have set, we are not violating any rule. We are following perfectly all the basic rules. Now, if we want to go for three-phase current source converter or current source inverter, then how many switches we need and what switches we need? Any guess? So what we have basically a current source, and what we have is basically three-phase load. Say RYB terminals are here. So now, what are the options? What can we have? Any guess can you make? How to connect this? So what was happening in the previous case is that whenever we are connecting this SPDT switch to any of the options, the current is either flowing through the load in this direction or the opposite direction, or even via the shorting terminals, but it is returning back to the source. So this loop is completed. Similar way, what will happen, instead of SPDT switch, we will have SPTT switch, single pole triple throw switch. So these three options will connect to the three terminals of the load. Say this is again A and B, and the options are say A1, A2, A3 and B1, B2, B3. This is what we are connecting to R, this is Y and this is B. Are you able to see this?
Yes, sir.
And to avoid any switching ripples and other unnecessary noise, we can connect some capacitor between all three phases. So making it little bit voltage stiff. Okay. Is that clear to all of you? So what will happen if A is connected to A1 and say B is connected to B3? So current will flow through this A1 to R, which means through this load R, and because B is connected to B3, So then to here, and then through this B terminal, it will return back to the source. So at a time, two phases will conduct. Any two phase. There is no further option for this to connect. So either R and B will conduct, or R and Y will conduct, or maybe Y and B will conduct, and so on. And direction can also be reversed. You can start from B and return through R. Are you understanding this point?
Yes, sir.
You want me to draw other waveform or other connections, or this is fine?
Yes, sir, fine.
Good. So this realization is happening through what is called a single pole triple throw switch. This is SPTT. And similarly, if you want to have more number of phases, what you need to do, you need to increase one more option for the pole here. Earlier we were increasing the number of throws. Here also we are increasing number of throws, but this is like each is connected to the load, the phase of the load, not the source. Okay, earlier it was connecting to the source. You understand the difference? Clear?
Yes, sir.
Yes, sir.
Yes.
Good. Now, the bigger question comes, how to realize these converters through the practical switches, which means IGBT diode and all that, right? That is the important thing to do now. So, okay, just a second. So again, we will follow the basic principles and we will see what switch can be connected to which place. Okay, it's a little bit heavier now. I need to delete some of the components in this. Okay, fine. So let us first realize the voltage source converter or voltage source inverter. So what we basically have in the voltage source converter, we have this kind of input and two options for the pole to be connected. Say R can be connected to R1 or R2. Now the question is, how much DC bus voltage we have? VDC. There is no doubt in that. The other property, because this is AC load, so we may have bidirectional flow of current irrespective of where we are connecting. Correct? This is fine, right? Now,
Yes.
two options are there for R. Now let us say when we are connecting R to R1, what we want from RR1, that direction of current can be bidirectional. So I is bidirectional. And about RR2, what is the polarity of voltage which it is blocking? So when R is connected to R1, what is the potential at this point?
Plus on R and minus on R2.
Say again.
Plus on R and minus on R2.
Yes, so plus VDC by 2 at R and minus VDC by 2 at R2. So total we are having blocking voltage of VDC. Notice the polarity. R is at the positive and R2 is at the negatives. The total difference is VDC. Now, the second option, what we have for our pole to be connected. Sorry. When it is connected here, RR2, again we have bidirectional current for the load. So current for this switch is again bidirectional. And what is the voltage blocking requirement for RR1?
So R1 plus R negative.
and total voltage is VDC. Correct? So what we need a switch which can block a voltage of VDC voltage level, and current should be bidirectional. Of course, the rating should be at whatever load we are connecting. So these two properties the switch must have, which means we are looking for a characteristic for both R1 and R2, something like this. We have one polarity, say, when we take R as no positive polarity. So this is the kind of requirement R1 is having. Okay, so this is blocking like plus minus voltage and current is bidirectional. Whereas our RR2 is blocking reverse polarity of that. You notice the direction, right? In first case, the R is at plus, the second case, R is at minus. So you can say that polarity is something like this. Understand the point? So what are the options here? Because we want unidirectional blocking and bidirectional current. So obviously we can have, let's say, an active switch connected with antiparallel diode, say IGBT connected to a diode. Now both are having similar properties, only the polarity of connections are different. So we may have a switch connection which is similar to, say, one switch over there, and just one second, fine. The second switch can come with this polarity at this point, and this could be our connection R. So say S1 and S2. When S1 is on, R will be connected to R1, which means our output VRO will be plus VDC by 2, because this point we are taking O. And S2 will be blocking how much voltage? V blocking will be equal to VDC, because this is at VDC by 2 and this is at minus VDC by 2. So total voltage blocking will be VDC. And because we have anti-parallel diode over here, so even if the switch is off, there can be a current in this direction. Or if we have positive current to flow, this switch is on, then it can go like this. Otherwise, the current can go like this. So irrespective of whether this is on or off, we can have current flow in both the directions. And similar thing is true for the bottom switch as well. This can also provide current in this direction or in this direction, and blocking in this polarity. Here the blocking is this polarity. Understanding my point?
Yes, sir.
So in a way we have created, if you see this total SPDT switch, what we have made over here, this has bidirectional voltage blocking and bidirectional current conduction. It can block positive voltage as well as negative voltage, and it can conduct in both the directions as a whole. Fine. So this could be the option when we want to realize our two-level converter. And just for a quick reference, I can draw the schematic of two-level three-phase voltage source converter. So we may have capacitor, fictitious point O, and these are the terminals for our three-phase connection. Correct? Similarly, if you want more number of phases, you can keep connecting like this. Say 5 phase, so 2 more branches or 2 more legs can come over here. Understanding my point? Fine?
Yes, sir.
Yes, sir.
Good. So we have realized the 3-phase voltage source converter and particularly 2-level. Now quickly let us see the current source converter. Now here if you see the requirement, when we have the current source, say we are talking about first the single phase only, and then we can extend that concept to 3-phase system. We have the pole which is having 2 options. Load is connected here. And say capacitor is connected here. So something like this. Now individually, if you see that this pole A and B, so when A is connected to A1, between A and A2, we may need to block either positive voltage or negative voltage. Because we are talking about AC load over here, right? So the polarity of voltage could be anywhere, depending on whether you are putting the lagging voltage or leading, lagging load or leading load, what kind of load you are having there. So for any blocking voltage, this may be asked to block any polarity of voltage. This is not defined. The only meaning is to say this, that if you ask the polarity of this voltage between A and A2, this is not defined, which means we should be prepared for both polarity of voltages. Whereas when you are connecting A and A1, the direction of current is fixed. It cannot be any other direction because we have current source over here which is having just one direction. Similarly, if you draw the other connection, so this part I am not disturbing, only I am changing this A to A2. This is connected over here. Now again, when you talk about this connection, from A to A2, the polarity of current is fixed. This cannot change because this is what the current source is giving. Whereas this voltage A to A1 is not defined. There is no stiff voltage source or anything which can define what is the voltage. So which means the polarity of blocking voltage could be both, either this way or this way. You understand the point? Now, what options could be there? So in case of A1, what we are finding that now our current direction is unique, is unipolar, whereas voltage blocking is bipolar. So this kind of characteristic we are looking for. Again, this also you can say that the direction of current is say going like this, and this voltage is also having bidirectional polarity. So this kind of switch now we are trying to realize. Is this point clear? Any confusion in this? Fine. So this kind of realization we may have by using the other arrangement what we have discussed earlier, by having active switch and anti-series diode. So what will happen? The direction of conduction for both the devices is same. So we have one direction for the current to flow. Whereas if you talk about the blocking voltage polarity, this device can block voltage in this polarity and the diode can block voltage in this polarity. So we have bidirectional or bipolar voltage blocking capability. Understanding my point?
Yes, sir.
So similarly, each of these switches A1, A2, B1, B2, all these can be realized. So if you draw the schematic of this single phase current source converter, okay, I think I need to adjust this thing. So what we have, instead of each connection what we were having, we have this kind of switch arrangement coming over there.
Sir, is there any problem to connect direct thyristor?
No, no problem.
Okay.
But we connect IGBT just because we want more control over there.
Okay, sir.
Thyristor turning off and no, all these arrangements you need to make. Here you remove the gate pulse, it is off.
Yes, sir. Commutation is required for thyristor.
Yes. Thyristor, like you can replace the entire thing with just one thyristor.
Yes, sir.
Because thyristor has naturally this characteristic, unidirectional voltage and bidirectional blocking. This is
Yes.
natural characteristic for thyristor. But only problem is the commutation.
Yes, sir.
You need to make some arrangement for that.
Yes,
So
sir. For
current
toggle.
source converter can alternatively be realized like this. In effect, this is behaving like a thyristor only, except the control part.
Then directly you can go for GTO, right? Like
GT also you can go. There is no problem.
because we can control in both the ways in that case.
Yes. And there is something called as switching frequency also, which we need to understand little bit
Yes,
later.
sir.
Hmm? So how fast you can control this device, that is another constraint. You cannot switch on, switch off at no much faster frequency. There is a lot of limitations. Okay, IGBT gives a lot of flexibility, and that is why we see that most of the industrial applications they are moving towards IGBT, no, towards let's say high power IGBTs, and then little bit more whichever was earlier working on GTO or thyristor based this kind of technologies, everything has slowly shifted to IGBT. Correct? Fine?
Yes, sir.
Okay. Now we just quickly draw the three-phase current source converter. So this was single phase. We have only two terminals for the load. Now if you have to connect say a three-phase CSI, you need SPTT. So SPTT is nothing but extension of this switch. There were two switches, now there are three switches like this. And this could be the return path. Fine. Where is the load? So load is connected from here. Like this. So you have either this say SR top or SR bottom. These switches are there. So either of this you connect. Then what will happen? It will flow into this R load, R phase of the load. If you connect both or turn on both, the current will simply circulate here. And at a time it will pass through two phases. Let's say you connect top over here and bottom over here. So it will enter into the R phase and return through the B phase of the load and then return back to the source. Or if you connect this here and this here, then it will enter from the top of this B phase and go to the B phase in positive direction and return through the R phase, bottom switch, and then here. Understand the point? Okay, and for having, say, absorbing some of the switching noises, we can connect capacitor across these load terminals. Sorry, not here. Something like this. So making the load little bit voltage stiff. This is the arrangement for current source converter. And you can have many more phases. You can keep increasing more branches and you can achieve more multi-phase CSI. So this is three-phase CSI. Fine. Any problem up to this? Yes or no?
No, sir.
No, sir.
Good. So now can you draw any schematic of any load or any this thing converter on your own without any problem?
Yes, sir.
Good. So then if you say so, let us try to draw the 3-level VSI. Okay, now you are confident, right? You can draw anything. Fine. So this is what we have. Three options for the pole to be connected, say R1, R2, R3. And we have DC bus midpoint at say 0 voltage. So negative is at minus VDC by 2, positive is at plus VDC by 2. Okay. Now let us realize this switches, how this is, right? Okay. So for this connection R to R1, what is the voltage when you connect R to R1?
Plus VDC by 2.
Plus VDC by 2. So under this condition, now because we are talking about AC load, so current can be bidirectional. So which means our R1 should be a bidirectional switch. There is no problem in that. Now what about the voltage blocking capability of RR2 and RR3? So what is the polarity between R and R2?
Plus on R and minus on
R positive and R2 negative.
R is positive and R2 is minus. And what is the magnitude?
VDC by 2.
VDC by 2.
By 2. Correct? Keep the numbers in mind very clearly, right? Now, between R and R3, what we have? What is the voltage blocking requirement first? Which one is the positive polarity?
R is positive.
R
R2
is positive polarity.
And magnitude?
VDC minus
VDC.
VDC by 2.
Magnitude is VDC. Okay. Now, let's go to the second connection. I need to draw this only for clarity. Otherwise, there is no need to draw it again and again. Okay, again. Now we have connection between R and R2. So what is the output voltage?
0.
0. Okay, under this condition, now what is the polarity for voltage? First, okay, current conduction. So current can be bidirectional here. So this switch must be bidirectional. Then what is the blocking capability requirement for RR1? Direction?
Minus VDC by 2.
No. First you tell which one is positive.
R1 is positive, R is negative.
R is negative.
Value is
VDC by 2.
VDC by 2.
2. Correct. About RR3, what is the polarity? Which one is positive?
R is positive and R3 is negative.
Value?
VDC by 2.
VDC by 2.
VDC by 2. Good. Now the third option. Okay. So what will be the output value?
Minus VDC by 2.
Minus VDC by 2. There is no doubt about it. Okay. Now the polarity is quickly. So first we take the current direction, which is bidirectional. So RR3 must be a bidirectional current switch. Sorry, switch. Okay. Now first between R and R1.
R1 positive and R is
R1
Value?
VDC.
VDC. RR2.
R is positive and R is negative.
Value?
VDC by 2.
VDC by 2.
VDC by 2. Correct? This understanding you have developed. Now you see clearly what is happening to these polarities. Here you have RR1 which is blocking plus VDC by 2. Here you have RR1 blocking plus VDC. Then you have RR2 blocking minus VDC by 2, you can say. Another place it is blocking plus VDC by 2. Third option, RR3 is blocking, say, minus VDC. And then it is blocking minus VDC by 2. The polarity is same, but the magnitude is different. You understand the point? So what we need basically, again, similar to drawing some conclusion from the previous voltage source converter, RR1 and RR3 can be simply drawn that, okay, if we take a switch, because capabilities we are drawing over here, RR1 and RR3, they are basically bidirectional current and unidirectional voltage. It's only matter of connection how you do. This is true for RR1 and RR3. But for RR2, we need both the polarities for the voltage and bidirectional current as well. Here the polarity is changing from this to this. So what to do? We can have arrangement like, say, for RR1 and RR3 as similar to what we have done in case of two-level VSI. This is what will give us unipolar blocking and bipolar current conduction. Now, if you want to have bipolar voltage blocking and bidirectional current conduction, then basically we need something called as parallel connection of this anti-series connection. This kind of arrangement is needed between R and R2 to have blocking in both the directions as well as conduction in both the directions. Do you understand this point?
Yes, sir. Yes, sir.
Correct. So quickly, if you mark the blocking polarities, these are the blocking polarities. The conduction, this can conduct here and this can conduct in this direction. So we have 4-quadrant switch drawn over here. Now using these switches, this one module here and the other module here, we can have our 3-level VSI, which is drawn or which can be drawn something like this.
Sir.
Yes, Ashish?
Sir, for series diode, if we'll remove this series diode, then also it will be bidirectional and so
But how will you have bipolarity voltage blocking?
Sir, yes. So, but connection is from positive to negative, and the next one is from negative to positive.
So basic principle, don't forget that this cannot block any opposite polarity.
Okay, sir.
This cannot block any opposite polarity. But which is why we need diode
Okay, sir.
to assist this. Okay. Now we have some connection or some schematic for the 3-level voltage source converter, which is something like this, right? There is no problem in that. If you have devices connected in this manner, yes, you can realize 3-level voltage source converter. You can add more branches, so have more number of phases, R phase, Y phase, B phase, and so on. Any problem in this? No, except that if you realize from the previous voltage blocking capability, what you have drawn is that R1, if you see, this is blocking something like either plus VDC by 2 or plus VDC. So maximum voltage blocking capability for RR1 is VDC. What is required from RR1 that it should block VDC voltage? Maximum. This is VDC by 2 in the intermediate level. This is VDC by 2. And which is also true for RR3. RR3 also need to block maximum VDC voltage, which is here. Whereas your RR2 switch, if you talk about, it is blocking only VDC by 2. Maybe polarity is different, but the magnitude is half. So when we are making something, let us say, at industrial level or even at our lab level, what we want some common devices. It cannot happen that some devices or some IGBTs have blocking capability of VDC and some other IGBTs have blocking capability of VDC by 2. So mismatch should not be there. Otherwise, what will happen by mistake if you connect this blocking at the middle and middle blocking at the top, then your converter will not work. No, it may get damaged. Understanding my point? So as of now, what we have here in the circuit basically is the blocking capability of this IGBT, which is connected here, is VDC. Blocking capability of this IGBT or diode also you can say is this VDC. Whereas here the IGBT diodes which are connected, the blocking capability is only VDC by 2. So there is mismatch in the blocking voltage or the rating of the device, you can say. Now to make it equal rating, let's say we want only VDC by 2 everywhere, we can connect one more device on the top and one more device on the bottom. So now our converter may look like this.
Sir,
Hmm.
sir, like for Q4 switch also we can like instead of realizing that Q4 switch we can use the ones that are used for RR1
Yeah, but
and in anti-series.
yeah,
In
but why?
anti-series. Like for uniformity, I'm saying like
That's
similar
what.
kind of switches.
This is like over designing your system. No, you need only VDC by 2 and you will connect a capacity of VDC, blocking capacity of VDC. Economically, that is not justified. No, you need only half. Why to connect more capacity for the device or more rating for the device? You understand the point?
Yes, sir.
So what we have basically that we can make all the ratings equal and we can have arrangement something like this. Okay. Now what we have, each device here is rated as blocking voltage capacity of VDC by 2. And here also all the devices are VDC by 2. Now we have uniformity. Now let us see what is happening in the circuit. Say we give some names to all these switches. Then we can understand better that what is happening with each of this switch. So first thing you realize that we have, let us say, switch 1, then 2, 3, 4. And say we are calling this as 2A and this as 3A. Something similar to what Professor Narayanan will call. So there is a particular reason why I am calling this as 2A and 3A. Now, what we have basically, the important point to notice, 2 and 2A are having common emitter connection. The emitter of both the devices are connected together. You see this point? Fine. And similarly for 3 and 3A, the collector are connected together. Correct? Fine, yes or no? Say something.
Yes, sir.
Okay. So here I need your attention a little bit. Now we have to understand what is happening with these devices, what voltage is coming across each device when we are operating in different voltage levels, and how the gating signals can be given. We have total 6 devices over here. So obviously we need to define how to give the voltage, gating signal for each device. So now let us say, if we have voltage output to be generated as, say, plus VDC by 2. So what will happen to the device 1, 2, 2A, 3, 3A, or maybe 3A I will write first and then 3. And 4. Okay, quickly you can tell what are the options, on and off options for these switches. Yes?
1 and 2 are
1
on.
and 2 are on.
Correct. So
Three
if
and
we
four
want to have plus VDC by 2 voltage, we must have 1 and 2 on. There is no doubt in that. It must connect, the R must connect to this positive DC bus voltage, and which is why these must be on. What about other devices? Okay, certainly we are connecting 1 and 2, so 3 and 4 must be
3
off.
and 4 are off.
Correct, there is no doubt in that. Otherwise you will short the entire DC bus. Now what about 2 and 3A? Again, you can only connect one voltage level at a time, right? You are connecting here, so you cannot connect to this point. So this also must be off. Correct, right?
Yes, sir.
Obviously, right? We are connecting with one voltage level. So in between, we cannot connect anything else. Now, let us see the next option. If we have to generate voltage 0. Now, which devices should be on and which devices should be off?
Either
2A
2 and 2A
2A or 3A.
To 2A or 3A, or maybe both we can connect. Any problem in that? Because current direction also we have to ensure, right?
Yes, sir.
If you have turned on 2A and current is in opposite direction, you have no path to make it flow. So we will ensure that both are on. Now any other thing can be off. Okay, now last option, minus VDC by 2. Tell quickly.
3 and 4.
Correct. This should be on. These all 4 should be off. Now
The 4 is
this
on.
should be on. Yes, correct. So 4 should be on. 3 and 4 are on for minus VDC by 2 realization. Now let us understand each scenario properly. When you are connecting this 1 and 2, basically, what is the voltage drop across these devices? 0. Because it is on. So voltage drop will be 0 volts. Here also 0 volts. Now when you are connecting or making this device off, the 2A is off, how much voltage will it block?
VDC by 2.
Sure? You see the polarity. It is positive here and negative here. Can this device block this voltage?
No, sir.
No, sir.
No. Then who is blocking that voltage?
3.
Diode.
No, 3 is in parallel. Who is blocking that voltage?
Sir, diode.
The diode.
Diode is there. So entire VDC by 2 is dropping here. Which means what is the voltage across this device? KVL has to be satisfied.
0.
0. So which means that if 0 voltage is coming across this device, whether you keep this device on or off, does it matter?
No, sir.
No, sir.
No, it doesn't matter. Now, but your 3A must be off. There is no doubt in that because this is the device which will stop voltage in this polarity, plus minus. Understanding my point? Here diode is not having any voltage drop because it has forward conduction in this polarity. Any doubt in this? So this is blocking VDC by 2. This is blocking VDC by 2. Now because voltage is equally divided for 3 and 4, this is also blocking VDC by 2. Understanding my point?
Yes, sir.
Yes or no?
Yes, sir.
Yes, sir.
Okay, next case if we go, we want to have 0 voltage at this point, at the output voltage R with respect to the midpoint O. So we have connected 2A and 3A. Fine. How much is the voltage blocking across 1?
Plus
VDC
VDC.
by 2.
Plus VDC.
VDC
VDC
by
by 2. There is no doubt because this is at higher potential, this is at lower potential. Again, because there are two devices and total voltage to be blocked over here is only VDC by 2. So maybe this is equally distributed if you turn off both. Correct? VDC by 4, VDC by 4. Now because we have devices which are rated for this voltage rating, VDC by 2, even if you don't turn off this device number 2, the device 1 alone is sufficient to block this voltage. Say by chance you don't turn it off. Keep it on. Doesn't matter. This one device itself is sufficient to block this voltage VDC by 2. This is the rating. Understanding my point? So we have the option to keep this device either on or off. Say we are keeping it on for some reason. Okay? Yes or no? Tell quickly.
Yes, sir.
Yes, sir.
Yes, sir.
Do you see this point or not? This is important. We are moving towards a very important connection. Do you understand this point?
Yes, sir.
Yes, sir.
Good. The yes should be confident. If you are not confident, immediately ask the doubt. Okay. Similarly, for this 3 and 4, how much voltage is required to be blocked in this state when you are generating 0 volts? In that condition, I'm asking. How much voltage is required to be blocked between this?
Sir, VDC by 2.
Sir,
VDC by 2. Which means what? Even if we turn on, or sorry, turn off this number 4 alone, this can block this voltage. We need not even turn off device number 3. There is no problem in that. If you don't turn off, still 4 can hold this voltage. That is the rating of that. So you have option to keep this device number 3 on during this state as well? Yes or no?
Yes, sir.
Yes, sir.
Okay, half people have disappeared from the screen. Deepak, are you finding this okay?
Yes, sir.
Neelam, you are missing from the screen.
Yes, sir.
Okay, any doubt, any question up to this, ask. No problem. Shall I go to next voltage output?
Yes.
Good. Now, when we are trying to have this voltage output of minus VDC by 2, what is the voltage blocking requirement for this end?
Plus VDC.
Plus VDC, which means we must turn off both 1 and 2 because rating is VDC by 2. We cannot avoid this. These two must be off and these two are on, so 0 volt is coming over here. Now, what is the requirement for blocking in this middle section?
VDC by 2.
VDC by 2.
VDC by 2. And what is the polarity? Now, this is at negative and this is at positive. You understand my point? Yes or not?
Yes, sir.
Yes, sir.
Yes.
Then can this device block that voltage 3A?
No, sir.
No.
No. Which device will block that?
Diode.
Diode.
Diode. So in this middle branch, in the lower half, the diode is blocking the entire voltage of VDC by 2, which means what is the voltage across this device?
0.
0.
0. So whether you keep this device on or off, this does not matter because this anyway cannot block any voltage. So simply we can keep it on. There is no problem in that. You understand the point?
Yes, sir.
Yes, sir.
Now what about 2? What about 2A?
So VDC by 2.
Must
This
be off.
must be off
On.
Yes.
because on the upper half, this is the device which is blocking this voltage, this polarity. It is positive here and negative here. So this must be off and the blocking voltage will come as VDC by 2. So much of blocking voltage device on and off. Now let us simplify what I am trying to draw, no, what conclusion I am trying to draw from this table. Now see little bit carefully. 2 and 2A are having very similar operation always. Do you see this? We have option for 2A, whether we can keep it on or off. So let's say we have on, then these two are nothing but operating together and the voltage drop is also same and the emitter, that means one terminal is common between the two. Similarly, between 3 and 3A, the voltage drop is equal and the operation is also very similar. We can have same gating signal for 3 and 3A. We can have same gating signal for 2 and 2A without any problem. Will we have any problem if we keep like that?
No, sir.
We will not have any problem. So which means gating signal for these two could be same and these two could be same. Now, even the voltage drop is also same. So can I make some arrangement in the circuit? Say I have 4 switches here. It takes little bit time to draw it every time. So just have the patience. Okay, what we are saying is that 1, 2, 3, 4, say 2A and 3A. What we are saying is that we are giving the same gating signal to 2 and 2A. And what we are observing from the table is that the drop across these devices is also same, and one terminal is actually common. So when the voltage at one terminal is already common, already same here, and other terminal is also going at the same voltage every time. So can I not connect these 2 points without any trouble? Can I connect?
Yes, sir.
Yes, sir.
Can connect, right? Potential is already same here at one terminal. Other terminal is also having same potential. When we say drop across the device, if that is equal and one terminal is having same voltage, which means that voltage at the other terminal is also same. So we can connect the points which are at the same potential with simply a wire without any problem. Similarly, for 3 and 3A, we can have connection like this. So what is happening? We have two IGBTs in parallel at these two places. We will have, right? We will have arrangement like this or not? Yes or no?
Yes, sir. Yes, sir.
Now we have said that the current flowing through this circuit is always bidirectional and same current is flowing through all the devices, which means the current capability or the current rating of each device is same and which is equal to the rating of the load. So which means actually we don't need two devices. One device itself is sufficient. So this device can get absorbed in this. So the remaining circuit what we will have after this arrangement, so this will get merged over here. This device and this device will get merged and this device and this device will get merged. And what we will have ultimately is the famous topology or famous circuit for 3-level converter, where you have 4 devices in the leg and diode connections coming over here. Don't forget, we have only merged the IGBTs. Diodes are still there. And these diodes are basically connected to the midpoint of the capacitor. Which converter is this?
Neutral point clamp.
NPC.
Correct. That is how the converter, what is known as neutral point clamped or diode clamped, all these names are given, 3-level voltage source converter. That is how this is evolved. It is not suddenly somebody woke up and started drawing this kind of circuit. That is how it has come up. You understand the point? Now when we have this understanding, we can go for higher levels, say 4 level, 5 level, 6 level, anything. You understand the point? And these levels can be divided by this capacitor bank. What voltage drop you are having across these capacitors. You can have more number of branches, so more number of phases can be shown over here. Clear? Now, when you have, say, 2 and 2A are merged, so that becomes 2, 3 and 3A are merged, so that becomes 3. So these 4 devices, now how these devices are operated, we have already given in our previous table. So which device is operated, which devices are operating together, which are complementary, you can see from here. So Always.
Sir,
Yes.
sir, two diodes are like clamping structure. That's why it is called neutral point
Yes.
clamp, or any other reason.
Now this is the reason. Clamping structure. The meaning of clamping structure is that this middle point will always hold the zero value, which means the voltage between these two capacitors will always be balanced because of this diode structure. If any time you have any unbalance, this will simply conduct and make it equal.
Okay, sir.
Okay.
Yes, sir.
Little more explanation can be given on this, but I leave it up to you. Just figure out how this clamping is coming. The result is that this voltage between these two capacitor banks is always going to be equal. It cannot be different.
Yes, sir.
That's the reason why it is called neutral point clamp. The neutral point is clamped to this value 0 always because of these diodes. So that's why sometimes it is called diode clamp.
Okay, sir.
Okay, so I leave this exercise up to you. Just figure out some literature or some other places why this is called clamp. What is happening if, let's say, I give an example that instead of this voltage being VDC by 2, say it becomes VDC by 2 plus X.
Yes,
And
sir.
so naturally the bottom half will have VDC by 2 minus X.
Minus X.
Total is still VDC.
Yes, sir.
But we have some unbalance of voltage X between the two halves.
So due to that, some circulating current may be flow, I think.
Figure it out and tell me.
Okay, sir.
Okay. So this is an exercise for all of you to do. Okay. Now here we have to see what is happening. See, if you observe closely, 2 and 2A are same. There is no problem in that. Whenever our device 1 is on, the device 3 is off. So we are keeping it like, whenever this is on, this device is off. And whenever this is off, this is on. You see this point?
Yes, sir.
Correct. Similarly, for 2 and 4, you can draw the conclusion that whenever this device, so take this option, whenever this is on, this is off. Whenever this is on here again this is off. And so what is happening in effect that our devices 1 and 3 are operating in complementary fashion. And 2 and 4 are operating in complementary fashion. In case of two-level converter, there is no problem. Both the devices are operating in complementary fashion. But here we have 4 devices where these two are complementary and these two are complementary. The meaning is that if you are giving gating pulse of say SA to this device, you can give SA bar to the device number 3. And if you are giving a gating pulse of SB, you can give SB bar to this device number 4. So only using 2 gating signals can operate this entire converter. Okay, other is only inverted form of the previous one. Of course, the other things which you know from your previous course at dead time and all these things, that has to be there. But more or less, these are related like this, in this manner. So whenever A is on or 1 is on, 3 will be off. Whenever this is the case. And whenever 2 is on, 4 will be off. These complementary switches can be off together, but they can never be on together. That is the condition. That is the bottom line. The meaning of complementary. Again, 2 and 4, sometimes they both can be off together, but they can never be on together. There must not be any overlap time between this and this device. We may have some blanking time or dead time between these two devices. Understanding my point? So before going into PWM, let me just quickly take this explanation of dead time, why this is required. So simple two-level converter can be used to explain that, what is meaning of dead time and why it is required, how much should be given. Say we have this converter or this leg of this converter, R phase, and we have two devices. So obviously we know that we are giving complementary signals to these two devices. Complementary signal means if S is something like this, on and off, then S bar is exactly inverted of that. So if this is S, this is S bar. Ideally, this is the case, what should be given to our converters. Understanding my point? Now what happens when we are dealing with the practical devices? There is some turn on time and turn off time associated with each device. So whenever you say turn on, the voltage may take some time to drop. If this is VCE, it will take some time to drop. Similarly, the turn off voltage may take some time to go off, right? Increase from 0 voltage to maximum voltage, VCE. Unless it reaches this off state, it cannot block any voltage. You understand my point? Unless the device reaches its off state, the IGBT cannot block any voltage. If it is somewhere in the middle, still the voltage is not, the device is not in condition to block this voltage what you are asking it to block, VDC. So what may happen if you are giving signals like this, while one device is turning off, the other may start turning on. And it may happen that because the turn on voltage many a time depends on the load. So while this is going to go off, the voltage will already be, this is going to go on. This still will take that time to go off. So at the same time, both devices may be on. You understand my point? You have given this signal at the same point. Whenever it is turning off, you have given this as turning on. So turn off may take time, and then still this has also come down to 0. So what will happen at that time? There may be a shoot through the DC bus. Both the devices are on together. So there may be a short circuit between the DC bus voltage itself, which is dangerous. That's why we need to give some blanking time, or which is also called dead time. Which means what we do basically, if this is our one device which is going off, the other device can only turn on after a certain time. We ensure that. So there is gap between the falling edge and the rising edge of the next device. Understanding my point?
Yes.
Again, when this device is going off and this is going on, we will delay this device. The incoming device is always delayed. So always the incoming pulse is delayed by certain time. Say some delta t or td or whatever you want to call. And this is typically of the order of say 2 microsecond to 4 microsecond based on the device. If device is slow, that means it takes a lot of time to turn off. That means we need to give more dead time. So any data sheet if you pick up, they will definitely talk about these times. Response time, delay time, turn off time, turn on time. These are the common terminologies written in the data sheet of the IGBT. From the moment when you give the gating pulse, in how much time the device is responding, that is a very important factor. So this is what the difference between the outgoing pulse and incoming pulse. This is what is called dead time or the blanking time, which we must ensure in case of voltage source inverter to avoid any kind of shoot through or short circuit through the DC bus. Otherwise, these pulses are complementary apart from this blanking time. Understand the point?
Yes, sir.
Yes, sir.
Clear? So this is the concept of dead time, which must be ensured in case of any voltage source converter. Otherwise, the devices or the gating signals are complementary in this manner for 2 level and in this manner for 3 level. Clear? Realization of all these things are clear to all of you?
Yes, sir.
Okay.
Yes, sir.
So because this was important point to discuss, no, in any power electronics course, at least somewhere you have to understand how the power converters are realized. That's why I have taken the entire lecture to only discuss this realization of VSI and CSI. So today we are not in condition to discuss the assignment. We don't have much time, but certainly if you have some questions about the lab exercise, I can answer those. So I stop the lecture here, and now we shift to your doubts or questions regarding the lab. Assignment we will discuss maybe in the next session. Okay, so again, before going to that lab exercise, any questions, any doubts up to this point? Do you have? I think I have taken very elaborate explanation of everything, right? Anything you feel that this is not discussed thoroughly? You need more explanation on that? Yes? Fine?
Yes, sir.
Okay.
Yes, sir.
Then let us come to the lab exercise. So Ashish was having one doubt, Ashish Kumar Panda, that how do we decide the limit on the integrators and other, wherever we have this, say PI is having 2 blocks. One is proportional, another is the integrator. So some gain times of integrator. Whenever you have integrator, you certainly need some value where you need to stop the integration. Otherwise, what will happen? Let's say your error is somewhere here. So integrator will start. It will start from 0 value. It will keep increasing. And by the time you feel that this value is sufficient, to actuate the power converter and the system, and the error starts reducing, by the time error reaches to 0 value, this will already be at very high value. Because integration means whenever the value is positive, this will keep increasing. You understand my point, right?
Yes, sir.
So this I am talking about the output of Ki. So Ki and integrator. Now, by the time this error has gone to 0, this is already at much higher value. So what will be the effect of that? You will start going in the negative direction. That means your output, which should have been here, now it will start going higher. So error is now negative. In response, this integrator will start coming down because now this is negative value. So integrator will start reducing its value slowly. And by the time it reaches to 0, again the error will be very high negative. And so what will happen? Your integrator will go to a very large negative value and then it will start coming back. Okay, it may not be such sharp this thing, it may be a smooth this kind of output. And so what will happen? Your output will never settle. It will always be either positive or negative error. This will continue. Because your integrator is not responding instantaneously. It is responding only on the basis of previous values. So this is called the problem of wind off. It is just running away from where it should be. So your response for the quantity may look like it is going very high positive, then very high negative, then again very high positive, like that, whereas the reference is here. So did any one of you observe this phenomena? Okay, none of you have done.
Yes, sir. Without integration, the value is increasing gradually.
Did you observe this thing, any of you? Okay, start doing the lab exercise. This is important because last moment when you do and see this kind of output, you will panic. Oh, this is not working. The KPKI values are wrong. Let me put something else. That's not the case. You have to understand the system when you are working with that. What you are computing is correct, but how to practically realize that in the system, that you should know. So what you need to do basically, you need to have a mechanism. Let's say you have error and this is increasing, but you cannot keep it increasing indefinitely. You have to have a value where it must stop, because this is enough. It can bring back this value to 0 if you give it some time. If you give it some time to respond. You understand my point? The other way to think of it is that you have a power converter, you are operating with a reference voltage. This is your reference voltage. And you are comparing with some sawtooth carrier. Now, this integrated response keep increasing means what? This V reference is increasing. And after some time, it will go here. That means permanently your converter is on. It is giving full voltage Vg. You understand my point? You have lost the control over this converter completely. So there must be some value, some limit for this Vref, how much it can go. How much it can go? Within the controllable range, it can go between 0 and 1. This is the
Yes,
peak
sir.
of your sawtooth carrier. So which means
Yes, sir.
your integrator output, whenever you are having current controller, the integrator output must be limited between 1, maybe -1 if you are going for negative direction. But as of now, we have not gone for the negative direction and all that. So keep it between 0 and 1. That is the saturation limit which you should have. And then again, for the total output also for the PI, that should be restricted between 0 and 1. Because which is what is your reference value. And if in the arrangement you have some feed forward term also added, EB by some K or whatever, then again the total value also should be restricted between this. In effect, the meaning is that you cannot have anything fed more than 1 to this comparison. You are losing the control. So yes, you may avoid maybe this saturation limit, you can avoid, you can keep something like 1 over here, but you certainly need some internal clamping for this internal saturation limit for the integrator. Otherwise, you keep this to 1, but internally this may be at very high value and it will take a lot of time to come down to the reasonable value. So integrator must have this limit of 1. This is for the current controller. So always the saturation limit is related to what quantity you are giving as output. Here your V reference is the output. Understand the point? If you have the speed controller, the same limit will be dictated by what quantity you are generating. You are generating the current reference. So for the speed controller, when you have P and then the integrator I, this limit will be restricted to plus IA or minus IA, which is the rated value. Minus because sometimes you need to reduce the speed, so you need a negative torque to do that. So for the negative torque, you need minus I rated value, negative I rated value. So here the limit will be between plus I rated and minus I rated. You understand this point or not?
Yes, sir.
Sir, I have one doubt, sir.
Yes.
Sir, actually, sir, I was simulating the current control loop. While I was comparing the actual current and the reference current, and then I was feeding it through the PI controller. Sir, should it be the value between 1 and 0 at the output at the PI controller? What we are getting?
Why?
It may be, sir.
Error in
Sir.
current. This is the
Yes,
error in current. This is actual value.
Yes, sir.
You are
And
subtracting current from current. You are getting the error, which is also current.
yes, sir. After the PI controller,
This is voltage.
the value that is voltage, but sir, its values will it be between 1 and 0, sir?
Yes, because this is voltage reference, no? You have to feed it to
It
the...
is voltage reference, yes.
Yes, so it must be between 0
mo-
and 1. Otherwise, how will you compare? This is the reference.
Sir,
yes,
one
sir.
in the
I
sense
understood.
one per unit, right?
See, when you say 1 per unit, yes, it is 1 per unit. But what is the base value for this?
DC-link.
Yes. So which is what we have done already. When you are designing these controllers, you have already divided by the DC bus voltage, VDC. If you see the expressions carefully, already VDC term is there. And when you are having feed
Yes,
for,
sir.
then also you are dividing by VDC.
Yes, sir. It's there, sir.
So automatically it is per unitized. That is the meaning to say that our sawtooth is going from 0 to 1. This 1 is the base value. And base value corresponds to VDC in this case. I'm not saying in all the cases.
Actually, sir, it means, sir, if we do the current control, then should I put the I reference in per unit value?
In? No,
Per
why?
unit value.
Why? I am talking about per unit of this section. Why? Because this is reference. You are comparing against this sawtooth. There is no such requirement of comparison in the previous block, no speed controller. Are you having any sawtooth or something to generate the current reference? No.
No, sir.
This is your actual current.
Yes, sir.
This is also your actual current which you are taking as feedback. But what you are generating here, this is actuating signal for your DC-DC converter.
Yes, which will be feeding to the gate signal of the MOSFET.
Yes, of course.
But sir, then also it was not coming, sir.
Check again. Discuss with the TAs. If everything comes so easy, then what's the challenge? What will you learn?
Hello.
Yes.
Sir, what is the permissible range of speed we can vary if the rated speed is 1000 RPM? Can we operate at a 100 RPM?
Yeah, you can operate. Anything below rated speed you can operate. But we
sir, one more question, sir.
Make sure you don't have provision for operating at negative speed. You are only providing positive voltage. So if you want to go for negative speed, do make arrangement in your converter for applying negative voltage as well. You understand my point? For a DC motor, having positive voltage, you cannot achieve negative speed, which means that flux direction is fixed. You are not changing the flux direction. Okay, so that's why we need to make arrangement in our converter if you want to go negative speed. Otherwise, anything between the rated speed is possible.
Yes, sir. And sir, one more question, sir. Sir, while I was doing the current control loop, what should load torque should be rated or anything I can put and it will be tracking what we want, sir?
Whatever I want, I have written in the assignment. It is up to you how you want to have. You have to understand. If you are starting any motor, okay,
Yes,
can you start with load? Of course, you can start.
Yes, sir. At node load, sir, it should start.
Why
But
it
at
should
that,
start at no load?
but sir, at
Can you
that
not
time, the
start at load? Is there any problem if you start at load?
no, sir. But at transient, it will be drawing current, sir.
Which transient, which current? You do and then tell me that this is what is coming. Then I can pinpoint the reason why it is coming. You understand the point? Sukumar? It is okay or not? You are looking lost somewhere. You are muted also, it seems. No, your mic is on, but you're not audible.
Audible, sir?
Slightly, little louder you need to speak. Yes, say, Sukumar, say something.
I saw the
Hmm?
that things are it,
Things are little bit?
that one there with
Okay, work through that and let me know in the next class again. Oh, you need to do it yourself once again. Watch the lecture again, it's anyway recorded, and do it once again yourself.